Our last speaker is Kunlin Wei. He's a professor in the motor control laboratory at Peking University in China. And his talk is titled Sensorimotor Adaptation by Task-Irrelevant Feedback. Stage is yours, Kunlin.
All right, let me find my PowerPoint. Share. Can you see it? Can you see my PowerPoint?
Yes, we can.
Great. So, it's great. JJ is in front of me, so I don't need to introduce a lot of background. So basically, we know visuomotor rotation. What JJ just showed is air clamp, and we know this is one typical type of sensorimotor adaptation. But people think it has two components. One is the implicit one, and one is the explicit strategy. Explicit strategy, basically, you can measure it by using those aiming report paradigm. And just before you're reaching for it, and you ask people where you're going, and that's the red cursor on the right graph, and your actual hand position is more deviated way if you are successfully adapt to visuomotor rotation. Then we can decompose the total learning into two parts. One is the explicit strategy part, one is implicit part one, which is a kind of unconscious, which is more sensory prediction error driven. Then indeed we can find this is one of the data set. So if we ask people to do visuomotor rotation twice, they will learn faster in the second time around. And if we look at it closely, as you can see, the black line is the total learning. That's your hand deviation. And you can decompose it into explicit part and implicit part. And during the second time adaptation, you will learn faster. Look at the black line, you learn faster. And also, people attribute to this kind of a saving effect as a recall. It's just a recall of your learned strategy, which is shown by the red line here. And my question in the current study is, I think there is a third component, that is, because when you are seeing this kind of a visuomotor transformation, which means cursor movement is deviated from the hand movement, and simultaneously, you kind of learn some conceptual knowledge of this kind of this visuomotor relation. Once you have this conceptual knowledge, it could lead to savings, leads to long-term effect of adaptation. So if that is the case, I can make three predictions. One is possible to learn or showing saving effect without adaptation itself, without forming strategy, without implicit learning. Once you know this concept, you should learn faster. The second time you see the same kind of cursor movement. The second hypothesis is, given its abstract nature, because it's kind of conceptual learning, this effect should be independent of error direction, error size, or even independent of task. I will show you later. My third prediction is not arbitrary visuomotor transformation can be learned. You have to learn similar concept to have this kind of effect. So what I do, I introduce so-called double cursor instead of a single cursor. Your hand is moving the green cursor forward, but there is task irrelevant cursor, which is the red cursor. The red cursor always goes, say, 30-degree clockwise or counterclockwise to your hand cursor. So instead of using air clamp, you can control the green cursor to hit the target all the time. So I call it double cursor. And the red cursor is the irrelevant feedback. I ask you to ignore it. And once you expose to this kind of double cursor, I can ask you to learn a regular visuomotor rotation. And how do people do? So this is a single cursor. Okay, here we go. So the first graph is the control group. You just see the first learning and the second learning. Indeed, people learn faster if they learn the visuomotor rotation twice. They learn 30-degree twice. And the second and the third graph are for the double cursor. For the double cursor, people can hit the target accurately because they have a green cursor to control. But once they learn the visuomotor rotation using a single cursor visuomotor rotation, you can see they learn much faster than the control group first time. And basically we see savings. And even sometimes the double cursor moving in the opposite direction, you see the same effect. All right. Then the other thing I have to point out is during the double cursor movement, there is no implicit learning because I can use catch trials, which is showing here. Where's my cursor? A catch trial basically shows people have no implicit learning, but they still exhibit a saving effect. So my second prediction is the effect should be size invariant. So I give some jitter to the double cursor. And in fact, the double cursor moving in some random directions, and it never covers a 30 degree, which is the angle that's showing the saving effect. And we found the same saving effect, which means the size doesn't matter here. Then the third experiment, as I said, I use a novel task, which is called a mirror reversal. Mirror reversal means your hand moving in one direction, but the cursor moving in the mirror-symmetrical direction. And here we have the same concept of visuomotor rotation, right? Then see how people react. Yes, people show saving again. And the other task is I change the visuomotor relation. I use so-called visuomotor gain. Visuomotor gain is another type of adaptation, but is different from rotation, different from directions. And I can show you the result. If you're using the mirror reversal, great, you can still show savings. But if you're using visuomotor gain, sorry, no savings, because the amplitude scaling is different from the direction rotation. So my take-home message is like this. So sensorimotor adaptation is possible, the same effect is possible without adaptation itself. There is no implicit learning. There is no actually to acquire some explicit strategy. And the effect is area direction independent, is also independent from size, task, but it has to be involve a similar rotation concept. So in fact, in motor learning, feedback is always task relevant, but task irrelevant feedback can also be learned. I think our study is the first study to show so. And but in visual perceptual learning, in fact, people found simply expose people to task irrelevant feedback, they can learn it. And so that's my talk. People can learn sensorimotor adaptation without actually learning it.
Okay, thank you very much, Kunlin. Again, if you... I'm muted. Oh, sorry. So again, if you have questions, put them in the Q&A or simply raise your hand and we'll put you on stage. Yeah, JJ, you had a question?
Yeah. Thanks, Kunlin. Very interesting talk. I was wondering, because so when you mentioned savings, is that for the explicit component or the implicit component as well? I mean, on the total adaptation, it was very clear, but I didn't know in your data which component showed saving.
Oh, sorry. I go through it too fast. It is an explicit component. You see the blue line?
Yeah.
They just learn, they got the strategy so quickly because they have the concept already.
Yeah, right. Yeah, but in your graphic, it was, there seems to be some difference in the implicit component, but I wasn't sure whether this was the case or not. Thanks.
Implicit component, I don't think so. Is more or less equivalent to the control group first learning.
Yeah. Okay, great. Thank you.
Sure.
Okay, thank you. Any more questions from the audience?
So maybe I can ask a second question while we're waiting then. So when you say, forming a concept, or, I mean, it's vague. I mean, so getting a sort of strategy, how do you see that exactly implemented? What type of system is that linked to working memory? Is that linked to, more the older literature on action observation? What do you think? What's the nature of that conceptual knowledge?
Yeah, that's a great question. For adaptation, people think it is more kind of low-level learning, right? And then we found that people can develop a strategy. But I think I go a step further, which conceptually is just because visuomotor rotation is too simple. And once you know the cursor can deviate from your hand in in different directions, you get this idea. Once you get this idea, it will impact your data. For example, I think this is a reminder to our field. For example, I just recently published a paper using the air clamp you just showed, and people learn air clamp, and then we test the saving effect. Yes, there is saving, but the air clamp is kind of implicit learning driven, right? But why there is saving? Then I realized because when we ask people to do air clamp, we ask them to ignore the cursor, ignore the task irrelevant feedback. Then they get the idea. They get the idea that the cursor could be moving in a different direction. They get the concept idea. That's why they show saving. My paper is published in Journal of Neurophysiology this year, but just this just prompted me to think, oh, maybe there is some other learning component we just ignored before, right? Because for explicit strategy, we have to learn it trial by trial. We learn it gradually, but the concept, you can get it instantaneously. It just reminds us visuomotor rotation is too simple for truly improving implicit adaptation. Yeah.
Yeah. Okay. So.
I'm sorry.
Oh, sorry. There's one question from the audience. So Barbara.
Hey, I have two short questions. Like the learning via implicit feedback you show here, is it equivalent to if you would tell the subjects that what the visuomotor rotation is? If you would tell them, oh, you have to aim 30-degree like counterclockwise? That's the first question. And the second question, like, I really like this idea of implicit and explicit feedback. But do you think this also applies to animals? Like if you look for visuomotor rotations in monkeys, for example, do you think, I mean, it's hard to test, right? But do you think they also have this explicit and implicit component?
Wow, that's a great question. So let me put it this way. My experimental paradigm is showing two cursors, right? But I think doing animal studies is too hard because our paradigm basically tell people to ignore one of the cursors, right? Even for air clamp, which is only showing a single cursor, we also need to tell people to ignore the cursor. But I believe in animal studies, you can test implicit adaptation very quickly because they don't understand the language, but once they control the hand cursor first, if they have a hand, then the hand cursor is moving in a irrelevant fashion, but that will introduce implicit learning because they still have surveillance, right? So, but for my double cursor paradigm, it's very hard because we have to use some kind of cognitive control saying, okay, please ignore the second cursor. But the single cursor one should be applicable to animal studies.
Thanks.
Sure.
Katinka,
you also had a question or comment?
Yeah, let's see what I can post very quickly. Thanks for fascinating work. I had to get my head around why the feedback was task irrelevant, but still relevant enough to learn from. And I wondered, is the key feature that it is movement that is correlated with your own movements? So would you still expect the same effects if the second cursor wasn't correlated with your own movements?
Oh, that's a great question. Yeah. It goes this way. In fact, that's something we can do next. If it's not temporarily coupled here, my guess is in certain window, you can still introduce implicit adaptation.
Okay.
But even though it's not time coupled, you can still get the concept because it's a spatial concept. So I will look at it in two different ways. Implicit learning really will be hampered by delay, saying the temporary delay, but the concept learning, no.
Yeah. Thanks.
Sure.
Okay, thank you everyone. So.